Howdy, hi, AP Calculus AB, and welcome back to our Topic 5 series on antiderivatives and integration. I'm sure you'll remember that the first, we'll say third of this unit was all about indefinite integrals and taking antiderivatives. We're in the midst of our second portion right now, which is all about definite integrals. We began definite integrals with how to find the exact area under the curve with nice geometric formulas. And then recently, the last few classes, we've been approximating area using rectangles or trapezoids. Finishing off this second part, we're going to try to make our approximations better, more accurate, maybe even the most accurate. To do that, though, we actually need to spend a few days on notation. And so we're kind of going to go into the past. Now, this lesson, the majority of it till we get to the end, will seem like review if you took a full year of pre-calculus. So we're going to be focusing on sigma notation. We'll go more into that shortly, but you can see a whole bunch of sigmas scattered over the page right now. However, if you took a shortened version, there's a chance you missed sigma notation in pre-calculus, so today might be a little new, but luckily it's not a crazy, tricky topic. So stick with me, and if there's anything more you need on this, I'd be happy to go through it with you later on. Let's begin. A sequence is a list of terms, and it's usually a list of terms with a pattern, at least the way we deal with it in math. So, for example, you'll see sequences oftentimes denoted in this a sub n notation, and an example of the outputs of a sequence might be 2, 4, 8, 16, so on and so forth. This n right here is counting the term number. So if we're looking at this sequence and I said, what is the second term? You might say, oh, a sub 2, the second term of the sequence called a is, what is the second term? Oh, that's 4. Right? Sequences typically, unless someone says something different, start with a first term. Technically, you can start with any term. You could say, and you just have to tell them, and we'll show you how to tell them that later on. You could say, I want this to be the third term. Well, then this one is going to be the fourth term, and you'd say the fourth term of the sequence is 4. They are commonly written in these curly braces to show you that there are no numbers in between, right? We use curly braces to list specific numbers, not intervals. And they also have what's known as a general term, where the general term is the formula for the sequence. And so you can see the general term listed in curly braces as well. Now, we also have what's known as a series. A series is a sum of a sequence. So if we wanted to look at the series for this sequence, then it would be as easy as adding up each term. 2 plus 4 plus 8 plus 16, right? That would be the series of the sequence out to 4 terms. A series is most commonly written using what's known as sigma notation. Right, sigma, and it's always, I am just great at butchering sigmas. It might be my single greatest gift to the mathematical community. So I'll do my best, and that was pretty good. This is the letter sigma, and it's the Greek letter sigma, obviously not the English letter sigma, because it's not in our alphabet, I think. I do have a friendly list here of all of our Greek letters, and I think if you continue in math, you should know probably all the symbols for Greek letters. You'll find, especially in college, the professors throw these out like they are the English alphabet. Yeah, so you should look at it. I don't know if anyone else learned the song for the Greek alphabet in 6th grade like I did, but that helps a little bit. It doesn't really teach you what the letters look like, but it teaches what you call, alpha, beta, gamma, delta, epsilon. I don't know. You can look them up later. So you have all these friendly Greek letters here where the uppercase, they did have upper and lowercase, uppercase on the left, lower on the right. You'll find that we usually use lowercase letters in math as variables. And uppercase letters usually stand for some, operation where like delta is change in, right? And as we go down, you can see the rest of these, right? Nothing too bad here. And we're still moving down. There's sigma. So this capital, and notice they give you the English equivalent. So this sigma is actually equivalent to our letter S. S sigma, that makes sense. And this sigma over here is the capital S, capital sigma in the Greek alphabet. You'll notice that there are two different lowercase ones, and I was curious what the asterisk meant, so I went on my own little journey. Second lowercase sigma letter is used in a final word position. So I assume that means if you're ending a word with an S, that you use one of them versus another. Either way, I would say that this one right here on the left is more common than the one on the right. I've actually never seen the one on the right. You use this a lot in statistics for your standard deviation. So either way, there's your quick rundown for Greek letters. Thought it was interesting though. So this is the Greek letter for capital S, and capital S makes sense because you're summing up a sequence, right? Now, how does it work? Well, there is a lower limit of summation and an upper limit of summation, and then the thing that is being summed, right? Our formula. Okay. Bonus, if you'd like, if you use your capital letter for pi, that means you multiply the series of a sequence, but this one is summing, and that's all we're going to do. So either way, we replaced our generic term for a sequence with the general term. And how does it work? Well, this summation ratchets up. It starts at whatever our lower limit is, and it adds, or it goes up by 1 by our natural number. So no decimals, no fractions, nothing weird, kind of nice. And it's going to take 1, plug it into the sequence, and give us our first term. Then it's going to say, okay, we used 1, so now we're done with that. Now we're going to use 2. It's going to plug it in, and that's our second term. And so on and so forth. And we're going to continue up to 3. And, of course, we're going to finish with 4. And how do we know we finish with 4? Because we finish once we hit the upper limit of summation there. It is a summation as well, which means after we go through and plug in all of those numbers, we actually have to add all of those numbers up. Okay? Did one calculation ahead of time, and we actually evaluated those numbers, and we found 30. Great. So today's class is split into 3 parts. The first part is just practicing each summation. The second part is how do we come up with the general term for a sequence. And then the last part is a little bit of a calculus connection. So here we go. I'm going to go ahead and give you, and this is going to be a lot of pause and restart sort of thing, but I'd like to give you a minute, 2 minutes, 3 minutes or so to work the first 4 questions. Your goal is to write each series in expanded form, which means writing it out like so, and then use your calculator to check the sum. As a heads up, I won't be using my calculator to check the sum, but you guys definitely should, and as always, please let me know if I made any mistakes. So, first 4 of these, ready, set, go. All right, and we're back to it. Now, it also maybe is worth mentioning that you can plug this straight into your calculator, but there's never a time on the AP exam where you have to use that. It's not one of your expected uses of a calculator, so you can look for that sigma or that summation on your calculator. All of them do it, whether it's a Casio, 84, Inspire, it's all there, and if you can't find it, just let me know. But what am I looking for here? Well, we're looking to substitute 1 in for n and go up to the 6th substitution, so it'll look something like this, right? Easy enough. You can, I'm sure, evaluate that out. It's going to be some fairly large number on your calculator. Okay, probably not even worth going through number 2, except realizing that it starts on 3. So you could do your 3 plus 1, which will give you 4/3, and then we substitute in 4. 4 plus 1 is 5/3, and I guess there aren't too many of these, right? 5 plus 1 is 6/3, and in fact, I'm doing these wrong. This should be 5/4 and 6/5, right? The numerator is always going to be 1 larger than the denominator, and so once you see the pattern, you might as well continue moving out. So that was 4, 5, 6. What am I going to end? We're going to end when there's a 7 in the denominator. So 7, 6 plus 8 sevens. Cool. The third one is a little bit more interesting, not so much in terms of evaluating or at least substituting in, but once you evaluate, you should know a couple things about this. This is actually a very, very commonly used sequence in Calc 2 and Calc BC. We do a lot with series here. So it's probably good to keep your brain a little fresh. We substitute in 0 first, and notice there's an x here, but we're not plugging anything for x. This says n equals 0, so this is just going to be x to the 0th over 0, and remember this exclamation mark, factorial, right? Remember those from probability, everyone's favorite. Then we have x to the first over 1 factorial, x squared cubed, and the 4th power. In terms of evaluations, I don't think we're going to use factorials this year, but again, good to know. Anything to the 0th power is 1. And then I'm actually going to come back to the factorials because I'd rather start at the end and work backwards just so we have a better idea of what's happening here. Probably should have left myself a bunch more space, but oh well. How do we do a factorial? Well, it's kind of like the opposite of this, and with multiplication. So 4 factorial means we multiply 4 times every whole number down until we get to 1. 1 is always our stopping point. So 3 factorial, 2 factorial, 1 factorial. What about 0 factorial? Well, this is more of a convenience, but 0 factorial is actually defined as 1. It's actually like a piecewise function where all of these follow this formula, and they just say when you get to 0 factorial, it's always 1. Why? And I mentioned it's a convenience. They really need it to be 1. They found that if it's not 1, a lot of things don't work very well in math, including probability, which is no good. Okay, and then our 4th one, just showing you that you could use a different variable in here. I think your book is actually very fond of I or J or something like that, but N is really the most common. So what does this look like though? Well, you substitute in 2, so we have 2 times 2 minus 1, and then we substitute in, I assume, 3, and I said I assume because it goes up to N. So how do we do that? Well, if you go up to n, if you don't actually have an upper limit of summation, it's pretty common to just do a plus ellipses, right, dot, 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 and then just say we're going to end with 2 times n minus 1. So that way if someone comes along and they say, ooh, I love this summation, they just replace n with a number, and then this just tells you to follow the formula out until you get to that value of n. Now, problem 4 that we just discussed really gives a series without an end, not no pun intended, end, haha. And sometimes you'll actually see this series written with an infinity as an upper limit of summation. So really the same thing as before. You're going to go ahead and write out, let's say, the first 4 terms of each infinite series below, called an infinite series because there's an infinity. I'm using k here as our variable, and we'll see what you come up with. And then unpause me once you're done. Ready, set, go. All right, so we'll work through these quickly, replacing k with 0 here, right? So we get 2 to the first plus x to the 0th, times x to the 0th, there we go, plus, and they asked for 4 terms, so notice we started with a k of 0 this time. You can start with any value if you want. K goes to 1, so that's 2 squared times x to the first. And notice this pattern of exponents. It's all about patterns today, and I think that'll make this go a little faster. It goes 1, 2, so this will be 3, 2, and then 4, 3. You can simplify that, but I'm not going to. We'll save that for the next one. Oh, and I should have done a plus dot, dot, dot. Very common if we're going to infinity. So, 6-1. Let's go ahead and all you work down below. So we have negative 1 to the first times cosine of pi times 1. And we're going out 4 terms. So negative 1 squared cosine of, instead of pi times 2, I'm going to write that as 2 pi. I think we're more used to seeing it that way. Negative 1 cubed times cosine of 3 pi. One more term. Negative 1 to the 4th cosine of 4 pi plus dot, dot, dot. And then simplifying down a bit, any negative 1 to an odd power is going to stay negative 1, so that'll stay negative. Okay, and any negative 1 to an even power, negative times a negative, will become a positive. So I'm just going to put those out there right now. And then we work cosines. What is the cosine of pi? The cosine of pi is negative 1. Cosine of 2 pi is 1. Cosine of 3 pi is negative 1. We just go back and forth, right? Cyclical here. It's in a cycle, something like this. So we can clean this up. So this just becomes 1 plus 1 plus 1 plus 1. Well, look at that. It's just 1 plus 1 plus 1 plus 1. Bet you wouldn't have expected that from that sequence. I think that's pretty cool. Moving on further, we have 2 more of these. So 0th power substituted in, negative 1 to the 0th, x to the 2 times 0 plus 1 is just going to be 1 here. over 2 times 0 plus 1 is 1 factorial. And then our next one, negative 1 to the first, now we're plugging in 1 now. 2 times 1 is 2, plus 1 is 3. And this is going to be 3 factorial. That's nice. Notice that the exponent matches the factorial down below. A little less math that we have to do. So I think this becomes much easier now, right? What are the powers going by here? Well, you might notice that the slope of this is 2, which means every time we increase our input by 1, the y's should go up by 2. So this one I think should be x to the 5th over 5 factorial. And then one more, and I somewhat ran out of room, so negative 1 cubed could go up by 2 this time, 7 factorial, dot, dot, dot. Okay. If you wanted to simplify again, take a look at what these negative 1 to different powers do. Anything to the 0th power is 1. X factorial over x over 1 factorial is just going to be x over 1. Negative 1 to an odd power is always going to be a negative, and this becomes x cubed over 3 factorial. The next one becomes positive. We're just alternating in sign here, aren't we? Isn't that what happened before too, I think? X to the 5th over 5 factorial. And the last one, we're going to switch again in sign. So actually that negative 1 to a power is very, very commonly used in sequences or series. We call them alternating series because the signs alternate every time, and I call this our alternating factor. It's the piece that causes our series to actually alternate in sign. I'm going to be very lazy here. There we go. The last one you're going to find is the exact same thing, right? There's no difference in these two. The only difference is in this. What's that going to do? Well, if you substitute 0 in for the first one, you'll get negative 1 to the first power. Over here we had negative 1 to the 0th power. To the first power is going to make the first term negative. Our first term was positive. So I think it's going to be exactly the same, just in a different color. It's going to be exactly the same as our original series from 7, except the signs are switched. It's going to be negative x over 1 plus x cubed over 3 times 2 times 1 minus x to the 5th over 5 times 4 times 3 times 2 times 1 plus, and you get the idea. So the signs are switched. Alrighty. This concludes really part 1 of our exploration today on sigma notation, and some of it went further than is necessary for this course. Some of it didn't go far enough, but I tried to pick problems that would at least be useful to you for next year or some that are relevant to this year. So let's go ahead. This second part right here asks us to work backwards. It says, we've given you a series. We want you to rewrite it using sigma notation. So that means at the end, all of these are going to have some sort of sigma. Don't forget to leave room at the bottom like I just didn't. You can start your sigma with any value you want. It is common to use n or k. I'm probably going to stick with n because I think that is more common. Your book might use k or j or something weird for this, but whatever sounds fun for you. You're going to need an upper limit, and you're going to need a general term. And in fact, what I find students struggle the most with here is coming up with this general term, writing a formula that fits a pattern, which is something we've actually been trying to prepare you for since like 6th grade, but I think we don't do a good enough job of trying to fit formulas to patterns. It's very isolated when we actually do that. So now we're going to make up for it by having you write formulas with many, many patterns, right? 8 of them actually. So I'm going to suggest that you try them on your own, or listen to me do one and then see if that helps you with a couple. Listen to me do the next, and so on and so forth. Okay, so let's go ahead and pause me, and then we'll come back together in just a sec. Ready, set, go. All right, the first thing you want to do when you're analyzing a pattern is you want to figure out what is the pattern. Make sure you can tell it to yourself in words or write it out in symbols, whatever sounds good. Oftentimes that's known as looking for a common difference or a ratio. A common difference is something with adding or subtracting, and a ratio is with multiplication. Technically division as well, but we tend to stick to multiplication just for convention's sake. So looking here, what is the pattern between the numbers? Well, we go up by 1 every time. This, in terms of sequences, is essentially the slope of our sequence. If we have a constant difference like that, it's going to be a linear function, And the slope of a linear function is very easy. The slope in this case is 1, so I know it's going to be 1n. All right, next thing I want to do is I want to make sure that if I substitute 1 in here, I get the first term that's happening up above. If I substitute in 1, 1 times 1 is 1, that is the first term. How exciting. What if I try 2? If I try 2 here, okay, 1 times 2 is 2, and that is the second term. That is also very exciting, and so on and so forth. Well, then the last piece of this, once we've determined our general term, is where do I stop? Oh, I think that's pretty easy. I think we stop at 6, don't we? Substitute in 1 to get 1, and so on and so forth. And of course, I'm sure someone's saying, well, couldn't I just write this as n equals 1 to 6? Yes, no problem at all. Okay. There are other ways to write this summation as well, so be careful with that. For example, I could have written this summation starting at 0. And instead of n, if we substitute 0n, that's certainly not 1, I could have done n plus 1. Substitute in 0, 0 plus 1 is 1. Cool. And then the next one's 1, substitute in 1, and 1 plus 1 is 2, and then we'd stop at 5. Right? So I'm not saying there's one right way to write this summation. I tend to start at 1, but I'd say 1 or 0 are both fairly common. All right. Keep trying these and then unpause me when you're ready. Okay. Problem 10 here is very similar to 9, where the first thing we do is we look at the common difference. And we should notice here that we go up by 2 every time. Going up by 2, that is the slope of my formula. I'm trying very hard on my summations here. So I'm going to go ahead and say that this is going to be 2n. The next part is we check it. If we substitute 1 in here, do we get the first term? And we don't. But don't be discouraged. We got the slope correct, so I haven't written anything incorrectly so far. We just need to adjust that. And how do we adjust it? With a constant. So if you substitute 1 in, 2 times 1 is 2. We want it to be 1, so what do you have to do to 2 to turn it into 1? You just need to subtract 1 off at the end. Now if we substitute in 1, we get 2 minus 1, which is 1. The next one we have to substitute in is 2. So if I substitute in 2, 2 times 2 is 4. 4 minus 1 is 3. Look at that. I think we found our pattern, no problem. How do we stop? Well, the easiest way to do it if you start at 1 is to just count 1, 2, 3, 4, 5, 6, 7, right? And then check. 14 minus 1 is 13. The other way you could do it is you could take your formula and set it equal to 13, right? Add 1. That'll give us 14, divide by 2, and we find that 14 is, or rather 13 is the 7th term. Okay, so let's move on. Why don't you guys try these next couple and then come back again? Hopefully this 11th one wasn't too terrible. You're starting to get the hang of things now. You're saying, ooh, look at this. It goes plus 2, plus 2, plus 2, so I know this is going to be 2n. We try plugging in 1. 2 times 1 is 2. That's good. Plug in 2. 2 times 4. Awesome. Super cool. But then we have to get up to 26. And you're like, ugh, do I really want to count all the way up there? No, let's just set 2n equal to 26. This is going to be 13, so we have to go 13 up. To check it, 13 times 2 does give us 26. Nice. The 12th one is, again, very similar. We're like, oh, it goes up by 2s. 3, 5, 7, 9. So we're going to go through, and we're just going to set that one first. Leave a little space in front here. So I know it's going to be 2n. We try substituting in 1. 2 times 1 is 2, not 3. So how do we bring 2 up to 3? We add 1. Okay, now if we try maybe 2 in here, 2 times 2 is 4. 4 plus 1 is 5. Good, so that's looking awesome. Just count these. 1, 2, 3, 4, 5, 6, 7. So we go up to the 7th term. 14 plus 1 is 15. That looks great, except one small thing. Oh yeah, we're alternating in sign here. First we subtract, then we add, then we subtract, then we add. Luckily we've seen that before. Let's just do -1 to the n and see if we're right. If we substitute 1 in here, that'll become a -1, and 1 in here becomes 3. Does it start with -3? No, it doesn't. Drat. What we've done is this formula right here would have written the pattern -3 plus 5 minus 7 plus 9, so on and so forth. So it's exactly right. It just switched all the signs. And I'm going to take a little bit more room here. So this was 2n plus 1 because the easiest way to flip the signs the other way is to just, instead of say this n, make it n plus 1. And now we'll be fine. If you substitute 1 in, 1 plus 1 is 2. Anything squared becomes positive, so we end up with positive 3. Plug in 2 here. 2 plus 1 is 3. Any negative 2 in odd power stays negative, and so we'll get -5. Yay! All right, a couple more to go. Let's see how you're doing. Ready, set, go. You might have looked at these last four and thought, ugh, fractions. Fractions are going to be the end of me. Fractions are easy. Fractions are just two patterns rolled into one. In fact, strangely, don't even think of these as fractions. Think of this as one summation for the top. There's one formula. And one summation for the bottom. There's a second formula. So when we go through and do this summation, pretty good. I'll again start at 1. I like to start at 1. It makes finding the top number a little bit easier, but sometimes you'll start at 0. Totally up to you. We're going to have a fraction, and there are going to be two parts to the fraction. The formula on the top of the fraction is easy. That's just a constant number. That's 1. The formula on the bottom of the fraction is a little more challenging, but it's not terrible. Let's just analyze the common difference. It looks like it goes up by 3 every time, so 3n. And then we'll see if we're right. We substitute 1 in for n. 3 times 1 is 3, not 2. How do we bring 3 down to 2? We subtract 1. Substitute in 2. 6 minus 1 is 5. Yeah, that looks pretty good. Where do we stop? 1, 2, 3, 4, 5, 6. We stop on the 6th term. Great. See? Fractions are easy. Fractions are our friends. All right. Why don't you try the next one and then unpause when you're ready. Okay, we're back. For this next one, again, it's a fraction, very exciting. So let's zoom in here. We are going to look at this. Here's my fraction, and we have two different patterns going on, one on the top, one on the bottom. I think the only weird thing, though, is this 1 right here. So let's see if we could maybe, instead of writing 1, follow the pattern backwards and see what should be there, and then see why it's 1. 8, 6, 4, 2. I think this one on the denominator should be 0 with a factorial. 8, 6, 4, 2. I think this one should be x to the 0th. But I think actually, as we saw earlier, anything to the 0th is 1, and 0 factorial is also 1, which is why they wrote 1 there. And it's very nice that they simplify it, but it doesn't actually help us. Now we have an idea of the pattern. What happens? Well, in the numerator, which I'll show in orange right here, there is x to some power. The x is constant every time, so there's just an x. But what happens to the power? It goes up, it looks like, by 2 every time, doesn't it? So this is going to be 2n. Let's start it at 1 and see if we're right so far. If we substitute 1 in here, 2 times 1 is 2, but we want it to be 0. So what do we do to 2n to bring it to, or 2 to bring it to 0? We subtract 2. Now if we plug in 1, 2 times 1 is 2, 2 minus 2 is 0. Great. If we plug in 2, 4 minus 2 is 2. That looks very good as well. Okay. And then what about if we did the denominator over here in blue? It looks like there's a factorial every time. That's good. And then, oh, it's just matching the exponents up above, so let's use the same formula as our exponent, putting that quantity in parentheses so we can see that it is all being, I guess the factorial is acting upon all of it. Okay. And then where do we stop? Well, first term, second, third, fourth, fifth, we stop at the 5th term. Quick check though, 10 minus 2 is 8, so we've done it right. Nice. I'm not going to go through these last two. I think you guys have the hang of it at this point, and there's nothing too crazy or different here. So go ahead and do those last two, and then once you're done, we'll move into our calculus connection, and we're done for the day. All right, welcome back. Let's do some calculus. So one of the main things we use sigma notation for in calculus is when we're doing approximations. And in particular, these Riemann sums that we've done the last few days are actually a little bit more efficiently written using sigma notation. So let's take a look at this. Write a left Riemann sum with 6 subintervals to represent the integral up here. You may leave your answer in product sum form using f of whatever notation. Okay, well, if we're going to do this, I'm not going to do the graph, but one thing I do really like to do, and I'm even going to leave off or just do kind of like a little tiny y-axis right here, I like to see my subdivisions. I think that helps me see the patterns. We're going from 1 to 4, and we need to subdivide that into 6 subintervals. Now, you could start, just putting little tick marks out there, but it's probably good practice for you to start finding your delta x each time, right? Length of the interval, 4 minus 1, split into 6 parts, and hopefully you can see that that is 3/6 or 1/2. So we need to go up by halves here, right? 1, and then we're going to split this into 6 parts, so it means 5 tick marks in the middle. That'll be a little bit challenging, but we'll do our best. 1, 2, 3, 4, 5 tick marks. Right? And then we go up by a half. So we have 1, and then we get 1.5, or I think we could say that's 3 halves. And then we add another half. That's 4 halves. And then another half, 5 halves. And yes, I realize we could reduce these, but the easier it is to see a consistent pattern from every single number, the easier today is going to get. 6 halves, 7 halves, and you might even think of 4 as 8 halves, and 1 as 2 halves. Okay, there are, and let's count how many values there are. 1, 2, 3, 4, 5, 6. There are 7 values for, of course, our 6 subintervals, because we're always going to exclude one of those if we do a left or a right Riemann sum. The nice part is the interval length is consistent. The interval length is 1/2. So if we wanted to take this integral and do 1 minus x squared dx, and I'm also at the top going to define f of x to be 1 minus x squared, so I can use that function notation. Then this is going to be approximated by 1/2. There's the base, and then we have a bunch of heights here. Okay, we need to use 6 out of the 7 heights, and it's a left Riemann sum. So we're going to start on the left and exclude the right endpoint. Okay, so what does this look like? We have f of 2 halves. That would be f of 1, and that would give us our first height. Then we have, of course, our base times our height. And then we have f of 3 halves. I'm going to need more space, but that's okay. F of 4 halves. And then we're going to go down here. F of 5 halves. 2 to go. F of 6 halves. And we finish on the ever so lovely f of 7 halves. Great. There is my left Riemann sum. But you might be looking and saying, wait, you didn't use sigma notation. You're right, because that's coming next. So, part B. Write your answer to A in sigma notation in 2 ways. First, using your f of whatever notation, and secondly, evaluating your formula in f of x equals 1 minus x squared. Okay, well, how do we use this in sigma notation? There's a couple ways to do it. I'm going to keep the 1/2 in this whole thing, and so we're going to do it like this. We're going to say we're going to find the integral from 1 to 4, 1 minus x squared dx, and it's going to be approximated by my summation. Okay, and then let's turn this into a pattern. Well, there's going to be a 1/2 there every time, and you could actually write the 1/2 out front, but I'll keep everything in the summation notation. So this way, it's really like I've distributed the 1/2 to everything, which I certainly didn't want to write down here, but that's what's going to happen up here. And then, what's the pattern? Well, the thing that stays constant every time is the f, right? F of something. And I should write this a little bit larger. F of something. And then pattern-wise, look, we finished with fractions inside. And so we know how to write the pattern for fractions. The denominator is always 2. Okay, if we're starting at 1 down here, the numerator, what's the pattern of the numerator? Well, we went from 2, 3, 4. It just goes up by 1 every time. So it's going to be 1n, or just n. And then let's see how we did here. If we substitute 1 in, does that match the first term? No, it doesn't. We need to increment or increase this by 1. If we plug 2 in, 2 plus 1 is 3, that's my next term, and so on and so forth. Great. That looks awesome. And then where do we stop? 1, 2, 3, 4, 5, 6. Oh yeah, 6 subintervals. This is a shorthand way to write our Riemann sum approximation. Well, how does that help you though? Oof, that's a great question here. We're actually going to go ahead and show you the answer to this in just a second. However, it did ask us to write this in a second way, and the second way is a little trickier, and it's something we haven't talked about yet. So the second way we're going to write this is like so. We're going to do that same sigma notation. There we go. Now my sigmas are going back to how I normally write them. But instead of f of something, don't forget that f of something really means take this thing and substitute it in for the x in our formula, or x is if there's more than 1. So I probably could rewrite this as 1 minus, and instead of x squared, substitute in n plus 1 over 2 squared. There we go. And what's going to end up happening now is now I have a formula that doesn't have f in it, and we could just substitute 1 in, do the math, and that'll give us our first rectangle. Then we plug in 2, and don't forget that this is all the height together. That's the math you do to find the height. And we have a base over here, and we plug in 2, and you get that next answer, and so on and so forth. Now, what does this actually look like? Well, I actually set it up on Desmos for you. So we have f of x equals 1 minus x squared, downward facing parabola, y-intercept of 1. I showed you what happens if we sum all of these up. I used decimals instead of fractions, but either way, I showed you what our approximation would be, so half of that. And then I showed it to you using our sigma notation. Now, I split the fraction apart. I'm not quite sure why I did that, but hopefully you can see if you put the fraction together, it's n plus 1 in the top over 2. F of n plus 1 over 2 with the 1/2 I factored out front for clarity, and you can see we get the same answer as if I had written it before. To do sigma notation on Desmos, by the way, you just type in SUM, sum, and as soon as you type it in, it gives you that sigma there. Alright, now you're not actually going to be asked to evaluate anything here. It's just practice writing all these different integrals and summations. So, let's look at C. Write a left Riemann sum with 8 subintervals to represent the integral. Okay, well, we'll do the same thing as before. Again, I sketch my nice little guy over here. This time, we are still going from 1, and I'll do this up above, learn from my mistakes, from 1 to 4, but now we want 8 subintervals. So how does that work? Well, delta x equals 4 minus 1, but divided by 8. Ugh, this is 3/8. Who picked this? But it gets better, I promise. Okay, so we're going to go through, and you can start with 1, but we'll actually come back to that. We're going to add 3/8 to the next one. So this is 1 and 3/8, but if we do our fun around the world, 8 times 1 is 8, plus 3 more is 11, that's 11/8. Okay, we add 3/8 to 11/8, that's going to give us 14/8, and I didn't give myself nearly enough room, but that's okay. Add 3 more, that's going to give us 17/8. And look at the pattern that's happening, right? Our numerator is increasing by 3, the denominator is staying the same. This is a left Riemann sum, so where do I stop? Well, we stop 1 before the 4, 1 subinterval, so 3/8 smaller than that is going to be 3 and 5/8, right? If you add 3/8, it brings you to 4, or 24 plus 5 more, we're going to stop at 29/8. Where do we start? Subtract 3, we start at 8/8. This, I think, will give us enough to approximate our integral, and so here we go. We're going from 1 to 4 of our, we're just going to say f of x dx, and saving some space. Each subinterval has a length of 3/8, right? That's what this delta x is over here. And then we start to plug things in, but I'm just going to use that f of notation. So we start with f of 8/8. And I'm going to be extremely lazy here, or we'll call it efficient, 11/8, right? F of 14/8, that's enough to see the pattern, and we're going to continue out until we get to f of 29/8. See? Not bad at all. Let's do our 2 sigma notations over here. Our first one, and trying to practice that integral each time. We're going to approximate. Forgot my approximately down here. We're going to approximate this. We need a summation. We are going from 1. We need our base, and then we need our height. Okay, so for our height, let's look at each of the heights down here. It's going to be f of something. I guess we don't need that extra parenthesis. It's going to be f of, and then each of these are fractions. The denominator is 8. That's wonderful. The numerator increases by 3 every time. So if we put 1 in here, 3 times 1 is 3, but I want it to be 8. Then we need to add 5 onto that. Right? Substitute 1 in. 3 plus 5 gets us 8. Cool. 2 in. 6 plus 5 is 11. We've done it. How far out? Well, we need 8 subintervals. And then that second step of showing you one more time, we are going to go through and replace, right? We're going to go from 1 to 8. We still have 3 8s here, but instead of f of this, we're going to substitute this into our 1 minus x squared. So 1 minus, what is x? 3n plus 5 over 8 squared. Nice. All right, we have 2 left, and there is a last page here, but that was if we had time, and we don't really have time. So if you want to try this one on the last page, it's a good problem, but we're just going to do 2 more of these and call it good for the day. So why don't you try them? These ones are right Riemann sums. We're pretty much already done with them. We've done everything we need up above. It should go quickly. Just remember the difference between a right versus a left. Try those 2, unpause me, and you're on the home stretch. Ready, set, go. Okay, I'm just going to refer to my graphs up above, my little mini graphs. Right Riemann sum, 6 subintervals, is going to do the exact same thing, but it's going to use the the right 6 values and exclude the beginning endpoint. Okay, so when we do this, we're going to have our integral from 1 to 4 of, well, again, call it f of x dx, and that's going to be approximated by 6 was nice, it had a length of 1/2 here, right? Then it's going to go f of, instead of 2 over 2, we're not starting at 1, I think we're going to start at 3/2, right? And then 4/2. And we're going to finish when we end up at the end over here, which is 8/2. And then we're going to put this in sigma notation. I should have given myself a little bit more room, but I'll just continue the approximately's. Sigma notation, 1 to whatever, 1/2. Okay, our formula is almost the same this time too. I don't need all those parentheses. We know that this is a 2 in the denominator. We go up by 1 every time. But now we're trying to start at 3. If we substitute in 1, it's just 1 to bring it up to 3. Add 2 more this time, and we need 6 subintervals. Okay? And you should practice substituting this in, so I will be a good teacher and do that as well. So we have 1 to 6, 1/2, and this was 1 minus x, in quotes, squared. See? Much faster. Last one, right Riemann sum. Well, we just kind of did that up above. Very, very similar. We're going to go, let's see if we can maybe even skip. No, it's probably worth showing this one more time. So, right Riemann sum, 3 8 this time. And our pattern over here is going to start with 11 8 this time and finish with, what's 4 in terms of 8s? Let's just add 3 8 more. I think that's 32 8. That's where we're going to finish. Okay, so it becomes f of my first term 11 8, 14 8, and then follows that pattern out to finish with 32 8. Cool. Sigma notation, we'll continue our approximately from 1 to something, 3, that's a 3, sure. Ugh, don't like that. 3 8 times f of what? What's a fraction? 8, we're going up by 3's, 3n. Substitute in 1, that's only 3. We need to get to 11. I think we need to add 8 more there. 2 is 6 and 8 is 14. Yeah, we're doing well. We wanted 8 subintervals. And finishing this off, 1, there's my usual sigma, my lazy, lazy sigma. 1 minus that thing squared. Whew. Now, why are we doing all of this? We're doing all of this to, again, find a better approximation. And what we're going to do over the next 2 classes is see how we can refine our formulas. And it's just so much faster and more efficient to write our formulas in summation notation than have to write out every term, that this is really going to be a lifesaver. And it's going to be able to show us how to find the exact area under the curve instead of just writing in a few rectangles. So thanks for sticking around, and I'm excited to have you back next class where we continue to bridge the gap of approximating area to finding the exact area.